Okay, let's restart. So basically, speed up, efficiency, scale up, and weak scaling. So these are a few definitions on how you can report, how you can quantify the progress you make when you actually parallelize an application. And the most well-known of such measures is the parallel speedup. So let's first start with a definition. So TPN is the time it takes to solve a problem of total size n with P processes. So P in this case can be the number of MPI processes, or it can be the number of threads. It can essentially be anything that is doing a computation in this particular application. And then the size n is basically the size of your problem. For instance, suppose that you are sorting an array, then of course n would be the size of that array. Suppose that you are computing a stencil code on a two-dimensional grid, then of course that would be the total grid size, so the number of points in that grid, and so on. So n is a measure for the size of the problem. P is the resources you use, so the number of processes, the number of cores which you're running your application with. Okay, so parallel speedup is the simplest definition, and you first measure the time it takes your problem to solve on one processor, so essentially sequential code. And then you divide that by the time it takes to solve it with P processors. So how fast does your code run if you run it in parallel? The ratio of those is the speed up. And of course, ideally, you would hope that the speed up is equal to P. That would be the ideal case. This is a measure which is often used, but one I'm not a particular fan of, and that many people are not a particular fan of, because it doesn't tell you the whole story. It gives you only that particular measure without you being able to interpret it directly in a proper way. So more interesting is the parallel efficiency, and that's just your speed up divided by the number of processes. And of course, that means that if your speed up is at best P, that's what you hope for. If you divide that by P, that means that the efficiency is somewhere between 1 and 0. And that means efficiency equal to 1 is kind of perfect. Efficiency less than 1 is, well, not so very good. Of course, there are very few applications that either reach a speed up of P or that reach an efficiency of 1. And that is quite clear. Any non-trivial application will almost always have a significantly less efficiency, an efficiency which is significantly less than 1. Okay, another measure is scale up, and that basically has to do with scaling up your problem size. So you look at a problem of size lowercase n, and here lowercase n is supposed to be less than uppercase n, so it's also your problem size. And you solve that problem with a single processor, and that takes a certain amount of time. Okay, then you actually solve a larger problem, but not with one processor, but with P processors. And those two times are equal. So you can solve a small problem on one processor, and that takes the same time as solving on P processors a problem that's larger, that's equal to capital N. Okay, then scale up is defined as the large problem size divided by the small problem size. And of course, you would hope that that scale up is in fact again of the order of P. Okay. So this is a different sort of scaling in a way. And then we have weak scaling, and to report on that, again, we have a small problem size n, which you can solve in time t1n. And then you scale that problem by the number of processors you are going to use. And the ratio of those two times, that's reported, and that is hopefully equal to 1. So that is something that shows you different scaling. Okay, so now a few problems there. Well, basically absolute megaflops rate, hardware peak performance, and so on. So essentially, how good are you with respect to the hardware you have? Because you can estimate how many floating point operations per second your application is doing. You also know or can measure the hardware peak performance. And basically, if your megaflops rate is way below the hardware peak performance, then you have to ask yourself questions. And that, of course, is something that is not quantified by speed up, the efficiency, the scale up, or the weak scaling. So that's something that still you have to check separately. What you can also have in some cases is superscalar speed up. So I mentioned that ideally the speed up is P. In fact, it can be a bit more than P, and that's a little bit bizarre at first sight. But on the other hand, that may happen due to the fact that you are going to decompose your domain across multiple processors. Each processor has its cache. So if suddenly the portion of the data it fits better into the available cache, then of course that would also speed up your application, and hence you may end up with a speed up which is in fact larger than P, or in other words, an efficiency that's larger than 1. So that is something that you have to take into account, that it may happen, and if that happens, then this is the explanation for it. Okay, and then of course you also have to consider whether SPN is close to P or whether it's quite a lot less. And again, I prefer efficiency. So if your efficiency is close to 0 or close to 20, 0.2 or something, then you're likely not very happy with the performance. So there are two laws here, and the first one is Amdahl's law. And to what Amdahl actually postulated was, okay, let's take the time it takes to solve a problem of size n with preprocessors. And you can break that down into two separate parts. One part is the fraction of the time it takes in serial code, in code that you for some reason can't parallelize. Okay, well, we already had an example of that. So our very silly example of computing the local boundaries for dealing with the domain, which you did just before the break, there was a serial part in that. The part where only process 0 was handling command line arguments, that was serial code. So that took up a fraction of the processing time. How much? Well, likely very, very little, but it might be substantial. So the lowercase f there, that represents the fraction between 0 and 1 of the total time of your application that is spent in serial code. Code that has not been parallelized, code that cannot be parallelized for whatever reason. Okay, of course, the second part of the sum, second term, is the part that can be parallelized. And then, of course, let's assume linear speed up, then of course that would be again t 1n divided by p, because we divide the work over p processes. And we assume even that this is perfect parallelization, perfect speed up. Okay, so if that's the case, then we can actually compute the speed up now in terms of this f. And then you see after some computation that you get 1 divided by f plus 1 minus f divided by p. Okay. So now imagine p being very large. Then essentially what we end up with for the parallel speedup is just 1 over f, because the second term in the denominator is 1 minus f divided by p. Let p go to infinity, or let p be very large, then that term in the sum is going to be negligible, and we're left with f in the denominator. So essentially that means that regardless of how large p grows, the speedup is always limited by 1 divided by the fraction of the code which is not parallelized, or more precisely, the fraction of the total wall time that is spent in code that is not parallelized. Okay, so that's a little annoying. But of course, yeah, how large should f be before we start to worry? So if f is, let's say, 10%, then of course you see that we get very bad behavior. So that's the red curve, the lowest one here. And you see that even for, let's say, 20 processes, we actually end up with a speed up of below 10, while the speed up should be 20. So we're already at an efficiency of less than 0.5, less than 50%. And the situation only grows worse, of course. For instance, for 40 processors, you see that we're still below a speed up of 10. So in other words, that means we have a parallel efficiency of only 25%. And we're nearly at the limit. So essentially for 100 processors, we would have, again, if I'm very generous here, a speed up of 10. So we're at 10% parallel efficiency. So this is really, really bad. But the situation is not that much better for half the time spent in serial code, 5%, because then that speed up is going to be less than 20. And you can see that even for 1%, it means that you can't hope to get more than a speed up of 100. And for 1000, not more than a speed up of 1000. So essentially that means that it certainly doesn't make sense to have p larger than our Amdahl limit, because that would be a waste of resources and you hardly gain anything anymore. So that is something to keep in mind. This is a fairly important law in parallel computing. Okay, so that is depressing, and to be honest, it's worse, because typically you also get contention, for instance, for your network. You get contention for your memory subsystem, and so on. So you're not even going to see this behavior. What is more likely is that the speed up reaches a maximum and then starts to drop due to inefficiencies and contention. So this is really not good news for parallel computing. So here's the same thing, but on a double logarithmic axis. Whatever, it's just the same thing, of course. Okay, however, what is good news, and let me go back here to weak scaling and scale up, So basically, that's actually what we're very often interested in. We're not so much interested in, okay, I have a problem, I solve it with twice the number of processors, does my time go down with half? Yeah, that's nice. But what we're typically in science even more interested in is, okay, I have a problem of size n, what happens if I double my problem size? That may mean, for instance, if I'm doing some stencil code, that I'll reduce my discretization by a factor of 2 or increase it depending on your point of view. So basically that you do your computations much more precisely. So that is what interests us. Or if we're into molecular dynamics, that we can simulate more atoms. So that is what interests us, and that is what weak scaling is about. So very often, we're not so much interested in parallel efficiency, or at least if it's not too bad, okay, but we're more interested in how things behave in terms of weak scaling, in terms of scale up. How much can I scale up my computations if I consider larger problems? And that is, in fact, another law, which is not mentioned here, but that is Gustafson's law. Okay, so let's talk a little bit about the history and how MPI is defined. So MPI is basically discussed, defined within the MPI forum. And so there was an MPI-1 forum. Let's not go too much into the details. What might be interesting is the history here. So the first MPI standard was published in June 1994. So basically, if memory serves, a year before OpenMP. And a year later, roughly, small changes were made in order to correct things, to clarify things, and so on. Okay, MPI2 forum. So they first did another minor revision of MPI1, and then they published MPI2. And there were a number of interesting extensions in MPI2 with respect to MPI1. And the MPI3 forum, MPI4 forum, as you can see, they started a couple of years after the publication of MPI2. That was 1997. So actually more than a decade later, people started to talk about MPI3. And so there were various iterations. Again, additions to MPI2 first, then MPI3 in 2012. And that was basically when I bought the book, which was just published then. Then there was a minor revision in 2015, and then in 2021, MPI4 was published. So basically, we'll also discuss some differences here. Okay. So scope and goals and such. So basically, the major goal is to provide a message passing interface. And a very important thing there is source code portability. So that basically means there are many implementations of the MPI standard. For instance, you have OpenMPI, you have Intel MPI, HPE creates its own MPI. I think it's even different from the one that Cray had at the time, and okay, still has on certain HPE systems. There are, I think NVIDIA has its own. I mean, there are quite a number of MPI implementations. Some of them, as you heard, are tied to certain vendors, like Intel, like HPE, like Cray, and others are open source, such as OpenMPI, but also, for instance, MPitch, MVPitch, etc., etc. So there are many implementations, and the nice thing is, since all of them implement the MPI standard, it means that your source code is going to build well and linked to any MPI library out there. So that's the good news. And of course, the MPI standard tries to give hints to efficient implementations. Actually, if you go into the specification, you will always see a number of perspectives there. There is, of course, the perspective of the programmer, and then you will see everything defined in a language agnostic way. Then for Fortran, for C, and you will also see hints to implementers, which basically means that's not for you if you're writing MPI programs, but that would be for those who are actually writing MPI libraries, I mean implementations of the MPI standard. And so even as a non-developer of MPI implementations, it's still interesting to read those hints because they often give you, let's say, a glimpse of what is going on behind the scenes in actual implementations, and that is at least interesting to know into that kind of thing, but also sometimes quite useful in order to understand why things work the way they work, what can be efficient, what is likely to be inefficient, and so on. So the MPI standard gives you a lot of functionality. We will cover quite a lot of things, and there's also support for heterogeneous parallel architectures, and that of course gets more interesting nowadays if we're talking about GPUs, other types of accelerators versus CPUs, and how they can do computations, all of them. Okay, so maybe let's not go too much into the history. So basically what we will discuss here is MPI 3 and MPI 4. If you have MPI 4 HPC, then of course this is MPI 3.1, 4.1. So essentially, we will be discussing performance quite a bit. The one thing which I'll say now and which I'll repeat a few times, we have source code portability. We don't have performance portability. So that basically means that if your code runs efficiently on a certain cluster, and you have to rebuild for another cluster with a different MPI implementation or with a different hardware architecture at network level, then you might have to tweak your application to get better performance. So that is unfortunately the bit of an issue with any parallel programming. You have the same thing with OpenMP. You also have the same thing with GPU programming. You have to have your hardware in mind. You have to do certain tweaks in order to get your application running at, well, the best performance you can achieve. But that means that you need to know the hardware, you need to know what you are using, and you need to know how to tweak things. Okay, so okay, there is a quiz here. Should we do that? Just have a look at it, I'd say. Okay, so there is a homework exercise, which is something that you could do tonight if you want. Okay, so let's talk a little bit specifically about code, because we have been talking a little bit about concepts, but we haven't seen much code yet, except for some fairly trivial examples. So let's go a bit more into details, so the process model and language bindings. Okay, so the first thing we need to do is, of course, to have the declarations of our functions, and in C and C++, let's include MPI.h. Okay, in Python, very easy. From MPI for Pi, import MPI. Okay, and in Fortran, you have a choice. Either you use MPI, or you use MPI F08. And if it's available, and normally it really should be available, and you should also have a recent Fortran compiler, then actually that is definitely the better choice, the MPI F08. And we will get into details why it is in a minute, and I think you will agree that it has quite some benefits. Okay, so the MPI function format, as I already mentioned, is very consistent. So basically, if you're talking C, C++, every MPI function will actually return an error code. So that's essentially an integer. If it's 0, everything went fine. If it was not okay, then error will be a non-zero value. However, you've seen me happily ignore that return code, that error value. That's because of something I also already mentioned this morning. Error handling in MPI usually means something goes wrong, abort. So typically there's not much sense in checking that error value, because internally your MPI function will have already noticed that something is blowing up and it's going to abort anyway. So that typically doesn't make too much sense. So mostly, almost always, you're just going to call that function and ignore the return value. So the name of the function, as I mentioned, always starts with MPI underscore, MPI in capitals, and then something, 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 a name, but the first character is going to be capitalized. So that's always the case for any and all MPI functions. So, very solid advice for C++ people, for C people, for Fortran people. Essentially, do not ever use anything as a variable name, as a function name, as a procedure name in Fortran, whatever, constants that start with MPI underscore whatever. Don't do that. I'm not sure whether I would have to verify. I'm not sure that the specification forbids it, but okay, if someone decides to add something, well, or no, let's rephrase. If the MPI forum decides to add a new function to the library, and it happens to be the name you gave your function, you are going to be in trouble. So the convention is never, ever have variable names, function names that you define that have MPI underscore as a prefix. Don't do that. Okay, so in Python, actually you have some MPI object on which you call a method, and that is going to return a value or an object or whatever. There is sort of, well, not so nice naming convention. I'm not really a big fan of it, but it's okay. I mean, you can understand it. And basically, the interface is modeled. The Python interface is modeled after what you used to have back in the days for C++. You might have noticed that the thing missing here is something specific for C++. And in fact, if you would check the MPI2 standard, then you would see that there were 3 APIs for each function. So the one was C, the other was C++, and the third was Fortran. However, the explicit C++ interface has been deprecated in MPI3. So yes, you can still use it. No, please don't, because it's going to go completely away at some point. So don't do that. However, the MPI for Python, the MPI for PyPeople decided to follow that pattern set by the specification in the days that there was the C++ interface and use that for Python, which sort of makes sense in a way. Okay, this is an example. We already saw that. The send receive thing we didn't see yet, but we will discuss it later on. Okay, and then Fortran, same thing. What I personally typically do, because you know Fortran is not case sensitive, so essentially you do whatever you want. But what I do, just to save myself from a lot of confusion, because obviously I switch from C to C++ to Fortran all the time. So essentially, I follow the same capitalization conventions in Fortran for MPI as are defined in C. So I'll do the exact same thing in Fortran. I just have MPI uppercase, underscore, uppercase, lowercase. So exactly the same as in C. If you feel differently about this, it doesn't matter. Fortran doesn't care, so you can do anything you like. But I prefer to save some brain cells from having to work by just following the same convention in C and in Fortran. Okay, so remember that rather than being a function as it is in C, in Fortran, this is all subroutines. So basically that means that that error value, which we're happily ignoring in C, has to be passed in. You need a variable that is able to get that value. So if you're using use MPI, then never, ever, never forget this I error. Because if you do, the MPI subroutine is going to write somewhere in memory the error value. It's going to do that. If you don't pass in a parameter, the compiler is not going to complain, and that error value is going to end up somewhere in memory, which is going to crash your application most likely later on, and good luck to you when you try to debug that. So do not forget ever to add this I error as long as you're using use MPI. So with the MPI FO8 module, so for Fortran 2008, you can actually omit error because it's an optional variable, and basically then you don't need to pass it in. So remember this is very important. Okay, so here you see a number of things. Essentially, yeah, of course, Python, as you know, is case sensitive, so basically pay attention to the things. So essentially, in C and C++, this is what we're going to use. So for the slides, Fortran will always be uppercase. Okay, MPI declarations will be mixed, and MPI constants will be uppercase, and that is for all programming languages the case, because that's convention in most programming languages. Okay, so sorry, in the examples, I'm still going to do the Fortran routines in mixed case as well. I'll do them the same. So that's a little bit different from the slides, but Fortran people know it doesn't matter anyway. So that out of the way. So basically, typically the errors are unused anyway, so you had to include MPI f.h, so that's even older, don't even consider that anymore. But this is also the case for use MPI. So if you then do a call MPI send and you forget the I error, you're going to be in deep trouble. So with the new module, you can actually leave it out because that I error is declared as optional in the interface. So this is already one motivation for always using MPI FO8. Which, by the way, I didn't up to now because I wanted to wait to discuss this in detail when we hit that particular slide. Okay, so essentially what you will pass in for C, and from now on I'm just going to, if I say C, I mean C and C++, but just to save some breath and some time, I'm just going to omit C++. So for the C++ people, if I say C, you mean that you know that I also mean C++. Okay, so basically, for instance, here we have a function call, and of course, you know that in C, by default, we've got call by value. So that means that if we want to modify something, the value of a variable, then we have to pass in the address. Hence, for instance, in MPI rank, the last argument is going to be a pointer to integer, not an integer. Okay. Similar, for instance, if we have MPI receive, the last argument is going to be a struct called MPI status, that's the type, but we also have to pass it in, if we create one, as an address. So for instance, here we have MPI status, receive status is the name of that variable. If we pass that into a receive, we have to pass it in as an address. So we use the ampersand operator to get the address of the receive status variable. Similar, rank is of course just an integer. If we want to obtain the rank using the the MPI rank function, we have to pass in the address of that variable. Okay. So basically, if you look at the index, write a number of indices defined at the end of the specification. So that's always so you can quite easily find that. If then we search, let's have a look. If we do model MPI command, I don't think you have to bother with capitalization. It will do the right thing. Yeah, it does the right thing anyway. So this is most likely for the MPI. So this is MPI. You see essentially a number of syntaxes. You've got D syntax. So you can see it returns an integer. That's your error code. It is an object of MPI and it takes a pointer to an integer. Fortran syntax. So this is use MPI. So no FO8. Then we've got our MPI rank subroutine. First argument is going to be an integer. Interesting. Second argument is going to be an integer. And third argument is going to be an integer. You already see that this is going to be annoying. So if you just use MPI, nearly everything is going to be an integer, which basically means that the compiler has no way to help you. If you accidentally mess up the order of the parameters which you use to call that subroutine, that's your problem. There is no, there is typing information here, but there is no distinction between a communicator and a rank or an IR. They're all integers. So compiler is pretty helpless. It can't tell you that you switched the communicator and the rank. So why are these integers? Well, basically, they are just indices into data structures that hold all the communicators. That's why a communicator is simply an integer in this particular Fortran syntax. So things improve quite a lot with Fortran 2008 syntax. Note we have to use MPI FO8. But then you see we have again our subroutine, communicator rank I error. So the communicator is of type MPI com. Ha, great. It also says intent in. So now we get much richer information for the compiler, and the rank is integer intent out. Yeah, that's exactly what we want. And then the error code is in fact also an integer, but optional, and the intent is also out. So now, of course, if you use MPI F08, the compiler has much more information. Because now, if you mess up the order and you would call MPI comRank with rank and then the communicator, then it would say, oh, this is wrong. Type checking says that the first argument should be of type MPI com and the second type is integer, and you switch them around. So that's wrong. So again, this is a very strong argument for using MPI F08. And then, of course, given that iError is optional, that means you can just leave it out entirely, which is good because you're not going to use it anyway. Okay, so that saves typing. And of course, much more importantly, it also means that you cannot forget about it. Or rather, that you can forget about it, but that's not going to bite you later on. And then you see here that there still is the C++ syntax. So essentially, you would call the getRank method on a communicator object. Okay, don't use this. As I already mentioned, it's deprecated. So that's a bad idea to start using it now. We'll see, because I don't remember exactly, we'll see later on in which MPI version it will really be removed. So now it's only deprecated. Okay, then you get the usual thing. So essentially, if you have normally MPI installed, and then you will have the man pages as well. Okay. So the MPI underscore namespace is reserved for MPI constants and functions and so on. So your own stuff should never start with MPI underscore. Okay, in Python, so MPI for Pi is not part of the MPI standard. Okay, and essentially it is a wrapper around the C bindings. And in case you're interested, that wrapping is actually done with Cython. So that's the approach they took for really optimal performance. Okay, well, at least back in the days. Maybe nowadays there would be better alternatives, but Cython will still be very good. Okay, so this is essentially a page out of the MPI specification. So you get a language independent definition. So that sorry, that just gives you the intent of each of the parameters. It also gives you a name that indicates what kind of thing it is and the semantics of that particular parameter. And then you have a specific C interface, the Fortran 2008 interface, and the old Fortran interface. So in MPI 3.1 and MPI 4, there is no longer the interface for C++. Okay. Then, as I mentioned, initializing MPI, you would have to call the MPI init function. And typically, at least in C, you will pass the address of argc and the address of argv, your command line, number of command line arguments and command line arguments as an array of characters, you would pass them into MPI init. So basically, MPI init at &argc, &argv. Okay. In Fortran, very easy, MPI init without any arguments if you're using F08, or with an iError if you're using old style use MPI. So basically, remember. Okay. Okay, we've already mentioned that. Sometimes it's optional. So normally if you are using an HPC cluster, and essentially you would say, well, okay, there are modules installed. Normally you can assume that the MPI implementation has been built with support for Fortran 2008. If you install it yourself, remember that there are MPI implementations, not to mention OpenMPI, that actually require you to switch on Fortran 2008 support. That was at least the case up to OpenMPI 3x. I don't know about 4x by heart, I would have to look it up. But essentially, if you're on a cluster, you normally don't have to worry. Your friendly system administrator will have done the right thing so that you can actually use the MPI F08 module. Okay, so for Python, you don't have to bother with MPI init. It's done automatically by importing the MPI module. So that is not required. Why? I already mentioned it. Under the hood, context is created and your whole program is running in that context. When the context is created, MPI init is run. When the context is exited, MPI finalize is run. And that's the nice thing about context managers. In Python, that's easy. If you use a context manager, such things are easy to do. Okay, here we have it. So basically, these are the different standards, and the colors indicate what you are supposed to do. Yellow indicates that something is deprecated, and red means it's being removed. So basically, orange is being deprecated. So if we look at include MPI.h, as you can see, it was valid and it was more or less consistent for a while, but it has been deprecated already in MPI 3, and it is, well, it is very much deprecated in, sorry, it's deprecated in MPI 4.1 actually. It was very strongly discouraged from MPI 3 onwards, and it's going to be removed in whatever comes next after MPI 4.1, so likely MPI 5. And as you can see, use MPI is sort of going the same route. So essentially it's now being, since MPI 4, being strongly discouraged to use, and it will get deprecated in the next release of the MPI standard. So basically, MPI F08 was introduced in MPI 3, and it's going to remain valid for quite a while. Okay, so essentially, I'd say always use MPI F08 for new code. Maybe you have to use MPI if you have to work with an existing code base which is older, let's put it that way. Okay, so exiting MPI, I already mentioned, you have to do MPI finalize, and that does not take any arguments, except in old style Fortran, you'd have to specify an error. And in Python, again, you don't have to do anything because that's called automatically. Okay, I already mentioned that MPI, there should not be any executable statement before MPI init. It's always the first thing you do. And MPI finalize is always the last thing you do. That's what the MPI standard actually says. So you can't do, it's better not to do anything at all. So then in MPI 4, you have on the one hand the world model, on the other hand the sessions model. But this we'll talk about later on in chapter 8. So for almost all applications, I'd say. You would have MPI init, you'd have MPI finalize. Okay. Why is it put here explicitly that there should not be an executable statement? Well, because back in the days, if you look at C89, you first had, if you got into a block, you had to declare your local variables in that block, and only then you could have an executable statement. So since C99, which every compiler supports C11, so certainly 99, that is no longer necessary. You can have variable declarations at any point of your code, obviously before you use them. So now I would say in C, just do MPI initialize as the first thing in your block, MPI finalize as the last thing in your block, except maybe a return 0 or something, and just declare your variables in between, and you're pretty sure that nothing will go wrong, even if you have code that actually calls functions to initialize things. Okay. So starting the MPI program means that you create quite a number of processes, and in a way, they sort of run independently, except that they exchange messages, and that's the way they interact. So you do that using, yeah, how should I put it? A start mechanism, start utility, and that is usually called MPI run or MPI exec. And then you can specify the number of processes and you specify your executable. Okay. And then, of course, the parallel MPI processes semantically exist as soon as MPI init was called. That's the idea. Okay. Right. Why this hello world thing is here is not entirely clear, because we already did an exercise which was more involved than this one. So let's maybe not bother, because that's not going to be particularly interesting, given all what we already did. Okay. Okay. So let's talk about the communicator. As you'll see later, you can have many communicators, but you always, in any MPI program, you have at least one, and that's MPI com world, and that contains all the processes. They'll get a rank in that communicator going from 0 to the number of processes -1, and each process can get its own rank using MPI com rank and the total number of processes with MPI com cent. MPI com size, sorry, not cent. Okay. So MPI com world is a handle or an object, depending on your point of view, which is defined in the MPI header and the MPI module for Fortran. Okay. And basically, handles, it's a word which we'll encounter quite a lot. Those refer to internal MPI data structures. So essentially, that could be user-defined types, that could be communicators, and so on. So you need data structures in order to represent those. Those data structures contain all the required information, and those are internal. So you don't need to know, and typically don't know, what they look like, how they are implemented. That is also entirely implementation dependent. So essentially, as a programmer, you don't care, but they take care of the bookkeeping of all the infrastructure, in a sense, which you need. Like, for instance, if I get a rank out of a communicator, the communicator out also knows how to physically reach that process, because you need an IP address, you need a port in order to communicate. So all of that is somewhere squirreled away into that communicator object. And of course, we don't have to care about it. Okay, so all MPI processes, application processes are started together. And of course, that includes all the software and the data. And they can actually communicate using that MPI COM world. So all of them live in MPI COM world. Okay. And basically, they will just check the MPI library. The MPI library will know how to communicate. Okay. I've essentially mentioned all this. So let's go to more handles. So handles identify MPI objects. So basically, they're either predefined constants or they can be objects. So for instance, MPI COM world will actually be a data structure that has all that information. And the same, of course, applies to MPI. So in that MPI module, there are a number of things predefined, such as, for instance, the COM world. Okay. So the type of MPI COM world is MPI COM. And in all reasonable implementations, and in Python, that would actually be the type of the object, which is here COM world, for instance. You can see that, okay, let's forget about the split here because that's a somewhat premature example. Okay, so essentially it's internal stuff. Right, how do we get the rank? We already saw that. We have MPI COM rank. We specify the communicator. We specify an address where to write the rank. In Fortran, same thing, but we have call by reference anyway, so we just need to specify the name of the variable in which we want to store the rank. And in Python, we just have the communicator object to which we apply getRank function. Notice uppercase, get. All right. So here's an example of call MPI COM rank, MPI COM world, my rank, and potentially IR, hopefully not. Okay, similar for size, no surprises here. So that gives you the total number of processes in your communicator. Okay. Okay. Right. Let's not go there. That does not matter. All right. So second exercise, which we're going to skip because that's exactly what we did this morning. So we're not going to bother with that now. We've already done that. Okay. So what we've seen is that the order in which the output was given is actually pretty arbitrary. So if I run, don't know which version this was, Fortran, yeah, Fortran. So essentially, in which order this output is going to be generated is runtime dependent. So in this case, actually, it seems, okay. So now, as you can see, it's different. First, we had rank 1. Here we had first rank 0. So essentially, we don't know in which order this is printed. And that's, of course, because the processes have slight delays with respect to one another. So one will do the printing first, and only then the second, etc., etc. So the question is there a way to ensure that the output is always going to be in the same order, for instance, in order of the ranks? Or is there no way to do that? So that's something that you can think about. I would say do this later on, and if you like, we can actually discuss that later. Okay, something that can be useful is to check which sort of bindings you have and so on. Do I have that in the repository? Let me have a look. Not entirely sure that I have that. Communicators, hello world. Load balance matrix, overlapping no. Let's have a look in hello world, it might be there. No, likely not. No, I don't seem to have it there. Okay, I'll add that at some point. But basically, that allows you to verify certain things about your MPI implementation. But unfortunately, I don't seem to have those defined here. No. Okay, never mind. Right. So now we know a little bit about our environments. We know about communicators, strength, size, and so on, but we didn't communicate yet. So how do we do that? Well, we already mentioned that the first way of doing that is by message passing and message passing from point to point. So basically, that's your most rudimentary way in which processes can communicate. So a message contains a number of elements of a particular data type. So MPI data types can be either basic data types or derived data types. And derived data types can be built up from basic or derived data types. So you can compose data types into derived data types, etc., etc. Any number of nestings essentially you want to do. So, of course, C types are different from Fortran types. And in Python, things get even more interesting because, yeah, yes, there are types, but they're sometimes very fluent. Let's put it that way. Everything has exactly the type, but you don't necessarily know what it is without checking. So the nice thing is that MPI actually gets its own types that are language dependent. And that basically means that you can actually map types from your, let's call it host language, to your MPI library. We'll see how to do that in C and in Fortran. So basically in Python, you can actually send arbitrary objects around. Not only basic data types, but all, which are in Python, by the way, objects, but also arbitrary objects, as long as you can serialize them. And serialization means pickling them. So that is a little bit different from C and Fortran, where if you wanted to send around an object, you would have to create a derived data type. So you don't have to do so in Python. Okay, so if your Python object supports the buffer protocol, which is the case, for instance, for NumPy arrays, then you can use other routines to send and receive, and those are capitalized. So we have two versions of send, one with lowercase, one with uppercase, two versions of receive, one with lowercase, one with uppercase. So anything you can send, anything that you send that supports the buffer protocol can be sent using the second type, and that will be very fast communication, while you can send arbitrary objects around as well. But then, of course, you would have serialization at the sending end, deserialization at the receiving end, and that may take time. Depending on how complicated your object is, that might be a bit of a problem. Okay, so we can send several data types. Let's go into this this example later on when we actually talk about, this is a good example. So a message could be, for instance, 5 integers. So the data types. So these are the basic data types for C and C++. In the second column, we have the C data type. In the first column, we have the corresponding MPI data type handle. So a character is MPI char, short, MPI short, int, long, signed character, unsigned short, etc., etc. All the combinations are there. MPI float is single precision. MPI double is double precision. You have MPI long double. You also have MPI byte. So that's to send sequences of bytes. Sometimes that might be useful. And you also have packed. So basically, we'll talk a little bit about packed later on. So in Python, you would have MPI float, etc. So basically, those are the type names of the usual things in Python, like a float, like an int, like a bool, like a string, etc., etc. Okay. Fortran has less types, which is not bad. So we have integer and MPI integer, real, MPI real, double precision, MPI double precision, etc., etc. So complex, which is directly supported in the Fortran language. We also have that. Boolean values, so logical, character values, that would be MPI character, MPI byte, and MPI packed. So further data types are, for instance, MPI real 8, which would mean 8 bytes reals, and that's basically double precision. So you would also have MPI real 4, for instance, for single precision. Yeah. I'm not so happy with MPI double precision, since in modern Fortran, using the double precision type is kind of looking weird, I'd say. I'd always use the kinds anyway, so in that respect, it's not so nice. Okay, so for instance, we could send 5 integers around, and they're stored in an array. And that would in fact be a single message with a count of 5 and the data type equal to MPI integer. Okay, so kind parameters are Fortran types, and actually you can create an MPI type, create F90 integer, and that allows you to create a type of a certain kind, which is of course convenient because then you can specify that you want an int 32, an int 16, or whatever, and you can create a corresponding MPI type handle. So that's quite convenient. Also for real and for complex. So that actually makes your code a bit more modern. Okay. So point-to-point communication is always between two processes. And you always have a source process that is going to send the message and the destination process that's going to receive the message. Communication of this type and of any type always uses a communicator. Okay, and then of course you specify the receiver or the sender using their corresponding ranks in that communicator. So for, for instance, if the whole thing here is our communicator and rank 3 is our source, it can send a message to rank 5. Okay, so what's the signature of our function? So we have MPI send. That is going to send the message, obviously. We specify the address of where the data is stored. We specify the count, and we specify the data type. Okay, so that's all about the data we are going to send. And then we need to specify the destination. That's an integer, and it's just the rank of where we want to send our message to. Then we have another integer, and that's a tag. We'll discuss tags in a minute. And the last argument is going to be our communicator. So in Fortran, we have, again, a buffer. And as you can see, that is, as can have any type. But of course, that should be corresponding to the data type which we specify. Then we have the count, and we have the data type. And as you can see, this is the FO8 interface. So basically everything is nicely typed, and the compiler can help you if needed. Okay, then in Python, the similar thing would be the buffer we want to send. If we have something that supports the buffer protocol, such as a NumPy array, then we have com.send with capital S. We of course have to specify the destination, and we optionally can specify a tag. If we want to send an arbitrary object, it's sent with lowercase, but also of course destination and tag. Okay, so buffer essentially is the starting point of the message with count elements. So essentially in C and C++, if you just have a single value to send, then you would just specify the address of the variable that stores it. Count would be 1. In similar in Fortran, of course, if you have an array or part of an array to send, of course you specify in C the address of the first element and the count you want to send. In Python, you don't have to bother because a buffer knows how long it is. So that's easy. If you want to send just part, yeah, you slice it. That's easy. An object, okay, if you can serialize it, so essentially if you can pickle it, then of course you also don't need to specify anything because then Python can figure out what that should be. Okay, so I already mentioned destination. That's just the rank where you want to send stuff, and the tag is additional information, so that can help distinguish between, for instance, different types of messages, because you might send messages to exchange data, you might also send messages to exchange state information, and if you want to distinguish for whatever reason, then you can give a tag. Of course, in C and Fortran, you have to provide a tag. In Python, you don't have to bother. There is a default tag, so you can use it if you want to. Okay, so do you need to actively use tags, essentially different tags for messages? Well, it depends on your application. Sometimes that can be useful. Sometimes you really don't care, and then you just give a default value for the tag, whatever it is. Okay, so that is the sending part. Now the receiving part, this has to be called by the process you send the message to. So it's MPI receive. Again, we provide the address in memory where we want to store the information. We give the count we give the data type. Okay. So, of course, there are some conditions which we will discuss later. Then we also specify where we expect that message to come from. Who is going to send it to us? So that's the rank of the sending process. And then we also specify the tag which we're expecting. And then the communicator and also the address of a status object. We will discuss this object in more detail. And of course, in Fortran, we've got something very similar. We have our address, we have our buffer, the count, the data type, etc., etc. So essentially, the exact same signature. Okay. I'm not going to distinguish each time between MPI F08 and old style. I'm just going to assume that by now you know. So I'm not going to talk about I-error anymore. You know what that means. Okay. So in Fortran, in Python, we again have two forms, uppercase, lowercase. So uppercase supports buffer protocol. So we simply set the buffer, specify the source, and the tag. And now you already see something interesting here. So all of these arguments, source, tag, and status, are in fact optional arguments. And there are some interesting differences. So any source basically means that I can to any source. So I can receive from an arbitrary process. And any tag means that actually I don't care which tag it is, I'll accept them all. And the status object, I don't need to specify. If I'm not interested in the status, I don't need to bother with it. Okay. And of course, if we are receiving arbitrary objects, again, same thing. Then, in that case, we don't even have to specify a buffer because the receive with lowercase function, well, method, I should say, is actually going to return the object anyway. So we don't specifically need a buffer here. We can omit that as well. Okay, and of course, for Python, we never need to specify the communicator because we're calling receive on the communicator object. So we don't need to specify that. Okay. I think that's pretty clear. So maybe a bit about status. What is the status? The status is in fact the envelope, and that contains some information about the message. For instance, it will contain the source, where it comes from. It will also contain the tag it has, and it will also have size information about the message sent. So that's in the envelope, and that is going to be returned in status. So sometimes that can be useful, sometimes you don't care. If you don't care, you can actually pass in MPI status ignore in C and Fortran. In case you don't care in Python, you just leave out the status argument, and then of course that is going to be ignored as well. Okay. Output arguments are printed in blue, so basically buffer is going to be an output argument and status is going to be an output argument. Now, I can hardly see that this is blue, but the out arguments are in fact also printed in italics. So for those of you who can't distinguish the colors, like in this case me as well, can hardly see the difference, you actually notice it because of the use of italics here. Okay, so the message matching rule, and this is important, the receiver, if he calls MPI receive, will only receive messages coming from the source he specified with the tag he specified. They must match unless, and the unless is on the next slide. But in theory, the count and the data type need not match. In practice, they almost always match, but they need not match according to the specification. So the message matching rule only is about they should be on the same communicator, yeah, obviously, and the source and the tag should match. Okay, there is an exception. Okay, there should be matching for Python actually. The send requires that the matching receive is a receive with capital. So capital S messages must be received by capital R receive, and of course a lowercase send must be matched to lowercase receive. That's an additional rule, which is fairly obvious, I would imagine. Okay, so a few requirements for point-to-point communication. The sender must specify a valid destination rank, so something between 0 and n-1 if n is the size of the communicator, and of course similar for the receiver. Otherwise, things don't make much sense. The communicator must be the same, pretty obvious. And we must have type matching. So essentially, if the buffer is float, now we're talking C, then of course the type, the data type handle for MPI should be MPI float. Those should match. Okay. Similar for the receiver, if we have a float buffer, then of course that should match the MPI float type handle. And preferably the type handles of the send and the receive should also match. So that's important. Then the tags must match as well. So essentially, for instance, if we have a tag 111 here, we're sending that, then of course the receiving tag should be 111 as well. Okay. Do you need to specify individual tags? Not necessarily. Maybe you don't need that information, and then the tag can always be the same value for all types of messages. So it depends on the application. Okay, so essentially that means that this velocity information is not going to be stored, not being received by any other receive than this one. So that's basically the idea here. And then the receiver's buffer must be large enough. So large enough means it needs to be larger or equal to in size as the sender's buffer. It cannot be smaller, but it can potentially be larger. Remember, of course, if you have a larger size at the receiving end, that you should likely initialize those values somehow in a different way. Of course, remember that we have the tag, we have the status, so we have the envelope of the message, and we can hence receive, we can check what we received, or rather, what the sender, how many elements the sender sent, and that can sometimes be useful in certain applications. Okay, if you have heterogeneous clusters, which fortunately you are somewhat unlikely to have, then of course it may be that your receive buffer and your send buffer need to do weird things depending on which hardware you're running. For instance, here is an example of having little endian versus big endian. Essentially, everyone has little endian nowadays, so okay, let's not really discuss this too much. At the moment, I don't think there are many heterogeneous clusters around, so okay, let's not do that. Okay, so we know how to send messages, we know how to receive messages, so now what we can do is do a ping. A ping is process 0 sending a message, process 1 receiving a message, and the axis down the page is in fact time. So obviously the receive in process 1 cannot precede the send in process 2, the event. Of course, the receive may be called before process 0 calls the send, but that is, of course, the flow of execution, not what actually happens in the code. Okay, so we're going to send a real or a float in Fortran or C, and we're sending a none in Python. Don't know why we're sending a none, but whatever. It's a list of one none. Oh, okay. Don't know why. Why not just send a float as well? Anyway, doesn't matter. Right, so this is the third argument, I think. So again, feel free to do the exercise. I'll slowly do one of them. Let me see what I have. So I've got already one in Fortran and one in all of them. So let me do the C one now for the ping, and maybe also the Python one. I'll not comment on what I do, so that if you want to do the exercise yourself, then I'm not disturbing you. Okay. So this would do a single ping. I'm checking the rank. Well, I'm defining the buffer, and I'm initializing the buffer for all processes to -1. Then I'm checking the rank, and if the rank is equal to 0, I set the send buffer to 3.14, so that only happens in rank 0. And then I'm doing an MPI send. I specify the address of the buffer. It's of course a single value, which is MPI float, and the destination is 1. I define a constant for the tag, which is 17, whatever, and MPI world. Okay, that's all the sender needs to do. The receiver will be rank 1, so I'm also checking for that. Then I do the MPI receive. I specify the address of a buffer. That is our float buffer in line 8. Okay, it's also receiving a single value, which is MPI float. It's going to receive that from rank 0. Again, we have a tag, we have MPI world, and we don't care about the status here, so I'm just putting MPI status ignore there. And then process 1 is going to print the buffer as well. Okay, so I'm going to modify a few things for clarity. So let's say we have int destination is 1, and we're going to put here destination rather than 1, and we're going to do similar. The source, source is going to be defined here as int source is equal to 0. Okay, and then just again for clarity, let's replace this by %d and by my rank. Okay. All right. So this ought to work. Let's see whether it does. MPI cc ping MPI run. And in this case, I want to run it with 2 processes. Okay. And as you can see, indeed, process 1 received 3.14 as intended. This still works if we run it with more processes, for instance with 6 processes. As you can see, we still get the right result. All the processes 2, 3, 4, 5 are not doing anything. But yeah, they are doing some stuff. What they are doing is lines 5 up to 9 and line 9 up to 20. So they're not involved in the communication. The only MPI thing they do is MPI init, MPI finalize, obviously, and the getting their rank. Okay. So essentially, this would potentially be my implementation. Okay. Should we also do that in a different programming language, or is it more or less clear? Let me perhaps do the Fortran one anyway, to use the new interface. That might be a good idea. So program ping. Okay. Then what else do we need? We need the real. Okay. Call MPI hits. Call MPI finalize. All right. Then call MPI com rank. Okay. And in fact, I don't need my size. So why I'm declaring it? Okay. We want to initialize the buffer for everyone to -1. Okay. And then if my rank equals 0, then I set the buffer to 3, not 14. I call MPI send, etc. I don't have a percent, so I'm fine with the buffer, but I'm not fine with everything. I want destination to be 1, but of course that means I need to declare destination and I need to declare source as well. Okay, so I want source to be 0, that's correct, and I want this to be destination, this to be the source. Oops. And I want the tag whatever. So that I can put tag here and make that a bit more explicit. Okay, let's wrap that around a little bit. Oops. Okay, and we print the buffer. Okay, not only that, process rank received buffer. Okay. So now we have the same thing in Fortran. Notice we don't have any I error anymore. We can get away with that because we have MPI F8. So that makes life a lot easier. Okay, so let's save it. Let's test whether it actually works. So let's print F90. Process rank, yeah, of course, stupid. That would be my rank. All right. Anything else? Yes. Tag 0. What? Tag 0. What did I do? Okay, that was stupid. Okay. Now happy. And MPI run. MP2. Take out. And as you can see, that also works. So it's quite easy to get that to work in anything. And I think you will agree that this code is a lot cleaner than it is with use MPI. So there is no reason not to do that in new code. Okay. All right, let's perhaps, unless there are any questions or require more time, let's maybe proceed with the slides. Okay, I'm going to assume that is the case. So basically, this is what we did, and we have an MPI receive, an MPI source, etc. So then the second exercise is that we are going to send a message from process 0 to process 1, and after receiving it, process 1 is going to send a message to process 0. So now we actually have a ping pong. Okay, so let's copy the code. And perhaps let me do that in Python this time. Essentially, it's the same thing, but so this would be the Python example. I've taken very explicit send and receive buffers here, so just to make the distinction between the two. And I'm using the lowercase version here because I'm just sending a single float, and most optional elements are left out. I'm not bothering with a tag in either send or receive, and I'm not bothering with status in receives. So I'm basically everything is at its default values here. Okay, so let's try to run that. Of course, should make sure it can run. So I have to make it executable, preferably lowercase u. Okay, here we go. And then MPI run -mp two processes with ping-pong pi. And something horrible goes wrong. What's up? Process exited to non-zero state. Okay, why? Module not found. Ah, okay. Yeah, I didn't load the module here. This is my Python window, and here I've got my MPI for Pi installed, so I can actually only do that here. And then you see indeed process 0 received the square of pi, well, almost, and process 1 received 3.14. So now process 0 is sending a message to process 1. Process 1 is sending a message to process 0. So hence ping pong. And of course, doing that in Fortran or in C would be very, very similar. All right. And then of course, this is just one ping pong. And then of course we can play that game many, many times. So basically, this is also a way to actually gauge point-to-point communication if we just time all this for many sends and receives. So for many ping pongs, then we can actually do that. Okay. All right. What you can do is overtaking. So basically, what is guaranteed by the MPI standard is that if process 0 sends two messages, then process 1 will first receive the message which was sent first by process 0, and then the message which was sent second by process 0. So processes actually never overtake. So that's a rule of MPI, and that's of the MPI standard, and that's of course in all the implementations. However, of course, what you can do is mess with that on one condition. So how might I receive a message that's sent later and receive it earlier than the second which was sent? How could I potentially do that? Any ideas? Exactly. You could use tags. So if, to stick with this example, if you would send the temperature with tag temp, well, sorry, with some value which represents temperature, and the other with a different tag, and then at receiving end, you first call the one which has tag mass, and the other has tag temp, then indeed they would seem to overtake, although actually they don't really. All right. So one thing which we already saw in the Python source, but which we didn't knew how to do yet in Fortran or in C, was using wildcards. So we would have any source in MPI for Pi. So here we have MPI any source, and that basically means that the receiver is listening or will accept messages that are sent by an arbitrary source. And we have a similar special value for any for tag, which is MPI any tag, and then it's just going to receive any tag. And then still, if you're interested, you can actually check which source sent the message and which tag that source actually gave to it. And this is stored in the status parameter, which is a data structure and which you can consult for these values. So this can sometimes be quite useful. Okay, so this is interesting. So in MPI 4, you can have assertions here. So you can assert, you can check whether this is in fact true, and whether this is true. So basically, to see whether that actually can be used. Okay. There are also other assertions about the tags. So normally, message can't overtake, but this may be overridden. And so you can check for whether that can be or not using these asserts here. Okay. But that is set with using MPI info, and that's something that we will talk about later. Okay. So, for instance, when would you use any? Yeah, and one thing I should really stress: these wildcards, by the way, can only be used in the receive statement, so never in the send statement. Can order of sending, receiving be chosen with these? No. So basically, then of course you can't really fiddle with the tag in order to influence the receiving order, because if it's any, then you can't distinguish. So of course that matters quite a lot. So then you really have to make sure that either you specify a specific tag if the order really matters, or that you deal with it somehow. So the overtaking, unless you switch that on, which normally is not the case, which you can only do in MPI 4 environment, but typically overtaking is not allowed. So if without MPI any tag, if you have MPI any tag, you have no control over that. That's basically the idea. And how can that lead to trouble? Maybe, okay, I never tried this, but we may have a go at it. So let me quickly, well, should I give an example of when that matters, or is that kind of clear? Okay, I'm assuming that it's clear. I don't need to give the example. If not, let me know. Okay. So again, wildcarding can only be used in the receive, never in the send, and it may be useful, but in some circumstances. For instance, one of the cases where it's useful, which is not really mentioned here, but for instance, if it's mentioned here actually, if you have some worker processes indeed. So if you have, for instance, a master that distributes work, then of course a worker may ask for work, and of course such message can come from any worker. As a master, I don't care. I just need to receive that message. From the tag, I can receive the source, I can retrieve the source, and then I can send work to that particular worker using the source tag in the status. And then, of course, I would indeed use this MPI any source. But of course, I would tag such a message because I might also receive messages from worker with results that they actually return a certain the result of a certain computation they did. And then, of course, I would distinguish between queries for work and submission of results by choosing different tags. for each of those messages. So in any case, I'd use MPI any source, but I would distinguish using explicit tags between a query for work and the submission of a result. So that's an example of using, on the one hand, a wildcard, and on the other hand, a specific tag to distinguish between type messages, message types rather. Okay. All right. So the communication envelope in C++, it's actually just a structure with a number of fields in it. So you have MPI source, and you have MPI tag, which means that you can retrieve those. And of course, in Fortran, with the latest interface, that's going to be an MPI status type, and that is a user-defined type, which has two fields, MPI source, MPI tag. Okay, the percentage sign, as you know, in Fortran means the same thing as the dot in C++. So basically, that's quite easy. You also get the MPI error, but okay, that's typically pretty useless. Okay, what you also get in addition is the actual count of the source element, although that is not mentioned here for some reason. Okay. Don't know why it's not mentioned here, but okay. And then in Python, we have that's an object, and you actually, it's not something like a tuple. It's actually a real object, and you can get the source, and you can get a tag. Okay, and you can also get MPI get count, but then you have to specify, you have to call the MPI get count message on that particular status object. Okay. So the receive message count in C and C++, you use MPI get count on a status object, which you pass in by address, and you specify the data type, and then it gives you the count. Similar for Fortran, and for MPI, you just give the data type, and it will give you the count. Note it will default to byte in Python, which is not necessarily interesting. Okay, so basically, let's have a look at this example. So this is Python. We have a NumPy array that consists of zeros. It's a one-dimensional array with 100 elements, and the D type is double precision, so essentially float 64. And we do a send, okay, of 5 of those. Okay, and we specify MPI double. So remember, we use send with capital S because this is a NumPy array, and hence it handles the it supports the buffer protocol, so I can use capital S. So at the receiving end, I have buffer, but I have a larger receive buffer. And again, I specify MPI double. Okay. I also specify the status, and then the count I can get from the status with MPI double, and then I do get 5. So of course, if I just would do get count, I'd get that size in bytes, and of course a double precision number has 8 bytes, so I would get 40 rather than 5. So that's why you have to supply that MPI data typing, because in fact the computations are done based on a size which in the MPI status object is scrolled away as a number of bytes. But of course you want it in terms of elements of a certain data type, and then of course that's why you have to specify the type here. Okay. Now, as we already mentioned, there are different communication modes, and up to now we've used MPI send. But a little bit tricky, because MPI send does a little bit what it wants. So we actually have a number of ways to do sends. For instance, if we want a synchronous send, we use MPI S send. And notice there is a capital S for the status, synchronous, and a capital S for, no, sorry, not a capital S for send. This is basically fortran notation. Then we can also have an asynchronous send or a buffered send, and that's with B send. Then the standard send, this is just MPI send, and then there's also a ready send. Okay, so there are for different use cases, and they may influence performance. For receive, the situation is quite simple. It's always MPI receive. So that's quite straightforward. Okay, so let's discuss that in a bit more detail. So if the send mode is synchronized send, then of course it will only complete when the receive has started. Note, when the receive has started, not when the receive is done. So the receiving party sends an acknowledgement as soon as the receive function is called. So that's with the MPI S send. Remember the Fox thing. Then we have the buffered send or the asynchronous send. So basically, the buffered send is going to complete as soon as it's safe to reuse the buffer, the send buffer. That's basically the idea. So that does not depend on whatever the receiver is doing. Okay, so you need an application-defined buffer in order to do that. So you have to do that with MPI buffer attach. And you can have automatic buffering and other buffering methods on communicator and session level, but that's new in MPI 4.1. So basically, there are some additional risks here. So there are some things which you have to be careful with, and especially in the context of Fortran, you have to be a bit careful. Okay, the standard send can choose whether it does a synchronous or a buffered send. So you don't know. Okay, and that basically uses an internal buffer if it's doing asynchronous I/O, so it's doing buffered I/O. And then finally, we have the ready send, and you can only do a ready send when the receive has already started. Okay, so this is pretty dangerous because this is a very nice way of creating race conditions. Because if you start your ready send before your MPI receive has been called, you have a problem. So yeah, this is really, really dangerous. Okay, then the receive, that will complete when you can use the receive buffer, essentially. And regardless of the MPI send you do, whether it's a synchronous send, a buffered send, a standard send, or a ready send, you always use the same MPI receive. Okay, so the standard send typically has the minimum transfer time for any message size, but it may block if it's going to synchronous mode. So essentially, it carries all the risks of synchronous send. Okay, we didn't talk about the risks of a synchronous send yet, but we will get there in a minute. Okay, so the synchronous send has the risk of a deadlock. It also has the risk of serialization and the risk of waiting and the risk of high latency, but it will give you the best bandwidth. So yeah. Then the buffered send, it has low latency, but it may have bad bandwidth. So yeah, typically you will get a minimal transfer time, but only for rather short messages. So as you can see, depending on whether messages are long or messages are short, you should either take asynchronous send or buffered send. And that's of course why we have the MPI send, because it knows the size of the buffer. That's easy to compute. It has in its parameters all the required information, and hence it can make an informed choice under the hood, of course, whether it's going to be synchronous or asynchronous, whether it's going to be a synchronous send or a buffered send. Okay, and then the ready send, we already mentioned that you really need to be sure that your MPI receive has already been called before you can actually do that. So it may be the fastest, but it's rather suicidal to use. So there will be a use case later, but typically this is a very dangerous one. Okay, so maybe a little bit about best practice here, or what I typically do, which may not be best practice, but which I consider as such. Usually when I start developing and I do point-to-point communication, which is not that common, that being said, I'll always start out by using asynchronous send explicitly, because it has a risk of deadlock. So I want to see the deadlock if there is one. It has a risk of serialization. I want to see it because this makes it explicit. If I would start with MPI send, then due to circumstances, due to the runtime, deadlock might not be triggered because it's not going to synchronous send. And then you go in production and you don't see any problems, you don't see any performance problems, and then you go into production. And then all of a sudden, your performance drops or you have a deadlock. So I prefer to see this up front. So I typically start with MPI S send, and then later on, when I'm convinced that there are no bugs anymore, I'm going to switch to MPI send to let the underlying library make the right decision. Okay, that being said, message order preservation. So as I already said, the rule for messages is that they will not overtake. We already mentioned should be on the same connection, so basically in the same communicator. We know the source and destination rank, etc., and they don't overtake. So that's also true for asynchronous sends. So that is just the rule, and the MPI implementation must ensure that that's the case. If both receives match, then the order is preserved. If you differentiate by tag, then of course it might seem that a message overtakes. Of course, actually it does not really do so. Okay. So I already mentioned that we can use ping pong as a benchmark, and there is a function MPI W time, so roll time, that actually measures time, gives you in double precision the timestamp since the number of seconds since 1st of January 1970 up to very reasonable precision. I think up to microseconds, I guess. So basically, the idea is time a number of ping pongs and see how much time it takes. And that gives you an idea about how long a message actually takes to send and receive. Okay, I noticed that I've overrun my time in the sense that we would have had a break 15 minutes ago. And I missed that. I tend to miss well, to not be a good timekeeper. So feel free, if I miss the time for a break, to just put a message in the chat. We want a break, and then of course I will immediately stop and let you have a break. Let's have a break now, and maybe what we can do is limit that break to 15 minutes. So resume according to schedule at 15:30, and then end a little bit early at 17:15. Has anyone objections to that? So does anyone really want a 30 minutes break? I'm happy to give you one. It's just that maybe it's better usage of time to limit the break to 15 minutes and then stop 15 minutes early according to schedule. So if someone wants a 30 minutes break, I'm happy to do so, but let me know in the chat. If not, I'm assuming that 15 minutes is fine and we resume at 15:30. Okay, 15:30 it is. I'll put that as usual on the whiteboard. And given that it's only a 15-minute break, I'm not going to pause the recording and just continue with that. So this would be 15:30. Okay. If there are any questions, feel free to put them in the chat as usual, and I'll answer them after the break. Okay, let's continue. I'll share my screen again. All right. And let's have a look at the ping pong benchmark. So essentially what you do is you send messages from process 0 to process 1 and vice versa. You do that a couple of times and you measure the total time, for instance, in process 0. You divide that by the number of messages which have been sent, and that gives you an idea about how long it takes to send a message. I don't think we particularly need to go into the details here. Essentially, that helps you to compute the latency for short messages. Okay, let me switch back to. Okay, so let's not do this one. It's not so very exciting to do. One of the things, if you do this, which you have to take into account, is that actually very often the first message takes a disproportionately long time. So what you typically do when you do this type of benchmarking is in fact that you do a number of ping pongs before you start measuring. And that's sort of a warm-up. So essentially it ensures that everything is nicely initialized and that you don't have, let's say, path-finding time for the first message. So that's the only thing which you would have to take into account. If you also want to measure bandwidth, in addition to latency, then of course you would have to vary the length of the message, so basically the message size. And then you can consider very short messages like 8 bytes, that would be one double precision value, or you can consider 512 bytes, so an array, 32K, 2 megabyte, and so on, because you will notice that the bandwidth will actually depend on the size of the message. So that's quite important if you experiment with that to actually do this. Okay. Apart from that, it's essentially just wrapping a for loop around our ping pong example and measuring the time. Okay. So perhaps let's skip this. I would say have a look at this quiz. If you have any questions about it, let me know, then we can go into that. All right. Any questions so far? Because maybe I haven't asked that enough. So let's give explicit time for questions now. Okay, not really. So let's turn our attention to non-blocking communication, because now we have considered blocking communication. Each routine, each function blocked up to a certain point. But we can also have non-blocking communication. So let's consider the following task. We have halo communication. Wait, there is something that maybe I should discuss in a bit more detail, or at least ask whether it's clear. So in this exercise, we are talking about latency and bandwidth. Is it clear what latency and bandwidth are? Should I explain that, or do you know? Okay, I'm going to assume you know. If not, you know. Okay, excellent. Then I can skip that. Okay, so we've got halo communication, and we're going to do that in one dimension. The story is the exact same in 2 dimensions, but at the end of the day, we can limit ourselves to 1 dimension to simplify things a little bit. So, as you remember, halo communication means that we need to exchange, let's say, the left side, well, it is the right side of our domain with our right side neighbor, and the neighbor needs to send the left side of his domain to the left side neighbor, and that's the idea. And now this comes in 2 forms, either with cyclic boundary conditions. So the last process is going to send its right side of the domain, the right end of the domain, to the first process in the communicator, and vice versa. Or we can have non-cyclic boundary conditions, and then there is simply nothing happening at the edge of the the left edge at the first process and the right edge at the second process. Essentially, doesn't matter much. Okay, so of course, if you go left to right and right to left, essentially it's the same thing as just going from left to right. So in terms of the arrows, that means let's concentrate on the blue communication. So basically going from the left to the right. The red one would be the same thing, but we can simplify. Okay, so essentially blocking routines run the risk of deadlock and serialization. So for instance, if we have cyclic boundary conditions, we do a send to the right rank, and we have to do a receive to the left rank, from the left rank. So basically, we're sending in only 1 direction, but of course we need to do a receive as well. Okay, so if we do an MPI send, we don't know whether it's going to be a synchronous send or an asynchronous send, a buffered send. But if it's a synchronous send, then of course the order in which we do the send and the receive really matters, because otherwise we have a problem. So basically, suppose that we are always doing the send first and then the receive. Okay, and we do have cyclic boundary conditions. Okay, so essentially, if this is a synchronous send, then the send is going to wait until the receive has started of rank 1. Rank 1's send is going to wait until rank 2 receive has started, etc., etc. So basically, if you look at the timeline, then you see a problem, because MPI send is waiting, MPI send is waiting, MPI send is waiting. Essentially, everyone is waiting, and we have a deadlock. Because the receives can't start. No one can start his receive, because everyone is waiting in the send for the receive of the next guy to start. That's never going to happen. So we have a deadlock. Okay, so where in OpenMP we would get only deadlocks when we had locks, explicit locks from the OMP library. Now, in this case, we have deadlocks when we do blocking point-to-point communication. So that's a risk. Of course, this would not happen if MPI send would choose to do a buffered send. Then that would not happen, but we don't know. So this can deadlock. Okay. If we have, of course, this is a consequence of the cyclic boundary conditions. But then again, what happens for non-cyclic boundary conditions? So, for instance, what we need to do is, if my rank is less than size minus 1, so essentially that means if we are anyone but the very last process, then we need to do a send. Last process doesn't need to do a send. Okay. If we are anyone except for the very first process, we need to do a receive, because the rank 0 is not going to receive anything from anyone. Okay, so again, if the library chooses a synchronous protocol, what we're going to have is, of course, that the send for rank 0 is going to wait for the receive of rank 1. But that's not going to start, because the send of rank 1 is going to wait for the receive of rank 2, which is not going to start, because the send of rank 2 is waiting for the receive of rank 3. Oh, finally, the receive of rank 3 can proceed. Then the receive of rank 2 can proceed, because it sends complete, etc., etc. So basically, what we get is essentially that everything will block until finally all the receives are done, and what we get at the end is serialization. Because the first process, rank 0, is going to wait until all the other sends are done. And rank 1 is going to have to wait until all sends and receives have started of all the processes to the right of it, and so on. So we get serialization, which is of course also very bad. So typically blocking routines, and especially if it's either an MPI synchronous send or an MPI send that happens to choose synchronous mode, then you can be in trouble. Either you have a deadlock or you have serialization. And of course, you only notice this, or this only happens, when you actually have a synchronous call. So that's what I meant when I said in the last chapter that personally, if I do these kind of things and I do choose to use blocking routines, then I will start off with MPI S send, so that I'm sure that I will see the deadlock and will see the serialization. So that is important to realize. Of course, the way around that is using non-blocking routines. So you could say, well, okay, yeah, deadlock, yeah, well, right, no, I'm going to simply avoid this. So what I'm going to do is to say, okay, all ranks except for the last one are going to do a send and then a receive. And the very last one is going to do a receive and then a send. Okay, that's nice. You've gotten rid of your deadlock, but you still have serialization. Why? Because everyone needs to wait until the receive of the last process has started. Only then the receive of the size -2 can start. Only then the receive of size -3 can start, etc., etc. So we do have serialization again. Another nice idea, you might think, is okay, I'm going to solve that differently. I'm going to solve that by saying, okay, all even ranks are first going to do a send and then a receive, and all alt ranks are going to do a receive and then a send. Okay, but then again, you get serialization because your neighboring processes are still going to wait for one another. So things are still going to block until you've got all your processes reaching the receive and completing their last send. So again, you've got serialization. Of course, each time only if the library chooses MPI S send, so the serial version, the synchronous version. Okay, so how to get around that? Well, basically, what you can do is non-blocking communication. So the communication is actually split into 3 phases. You initiate non-blocking communication, that's phase number 1, so that returns immediately. And the routines for doing that start with MPI underscore I, capital I. Okay, and this is a local operation. So basically, it returns independently of other process activity. All right. Then the second phase, do something, whatever, that involves perhaps doing other communications or computations or mining bitcoins, whatever. And then you wait for the non-blocking communication to complete. And you can do that. In that case, you can, after that, you can be sure that the send buffer is read out in case that you have a non-blocking send, or that the receive buffer is filled in if you have a non-blocking receive. So those are the three phases. And as opposed to the modes of communication for blocking communication, where you had only when you had a receive, here we can also have a non-blocking receive. So here we can do non-blocking send. We can do non-blocking send. We can do non-blocking receive, or we can choose either of them. So we can mix and match depending on what we want. Okay. So the I here in MPI I something stands for either immediate or incomplete, whatever you like. Anyway, it's non-blocking. Okay. So some examples. A non-blocking send. So 0 is going to send, and it's going to use an I send. Okay. So essentially, it's going to do some work, and then it's going to call MPI wait, and that will block until the MPI send is done. That means until it's safe to reuse the buffer that was the send buffer. That's essentially the idea. So a non-blocking receive, for instance, now process 1 is going to receive. So it's going to do an MPI I receive. So that just signals, okay, I'm ready to receive. Meanwhile, it's going to do other stuff. And then at the end of the day, it's going to call again an MPI wait, which will block until the receive buffer has been filled and it's safe to use it. Okay. So the triple line thing actually means waiting until the operation is completed. So MPI wait is the one which actually blocks until the operation is completed. And between the MPI I whatever and the corresponding MPI wait, you're free to do whatever you want. Okay. So a non-blocking send, you initialize it. And so in the ring example, you initialize non-blocking sends to the right neighbor. You do something. So in this case, receiving something from your left neighbor. And then you just wait until everything is completed. Okay, so how would that work? Everyone is going to do an MPI I send. Okay. Since that is non-blocking, you can then immediately do an MPI receive. Okay. Then you wait for those to complete. That's essentially the ID in a non-blocking send. And you can do similar for a non-blocking receive. So what you can do is initiate a non-blocking receive, then do whatever you want. So in this case, send something to your neighbor. The message transfer can complete, and you wait for non-blocking receive to complete. So essentially, this is the receive, non-blocking receive. Those are the sends. Everyone is happy. The transfer can be completed, and we wait for completion. Okay, done, ready to go. Okay. So this means that we will not have serialization and we won't have deadlock. So these are the diagrams that actually illustrate this. So this is, for instance, the MPI I send. This is the MPI receive. That's the MPI wait here. And as you can see, all processes finish the MPI wait at approximately the same time. This would be the corresponding thing, but now with a non-blocking receive. So we have a non-blocking receive here. So the receive is initiated. Then we get a send, which is blocking, but which can be either synchronous or buffered. And then we have the corresponding MPI wait. And again, no serialization, no deadlock. So this seems like a very good idea. And basically, it's a quite nice approach. But of course, there are some caveats here. Okay, so we can again do an exercise, and that's rotating information around in a ring. This is an exercise which we definitely will do, because we will review later on. Okay, so it's also the smallest possible example of what would be halo communication, not hello, halo communication. So send buffer is the data that is sent to the neighbor, and the receive buffer represents the halo. Okay, so essentially that would mean that the send buffer is indeed the actual data of our domain, and the receive buffer is the halo in the neighbor. Okay, and of course we're not going to bother with huge double precision arrays, but just with a single integer will also do. And it's communicating in a ring essentially. So okay, we'll start with MPI send and MPI receive. So let's do that first. Okay, so let's go to, for instance, let me see, what have we got? So we have one Fortran, okay, one non-trivial Fortran. Okay, we don't have, okay, we have a somewhat non-trivial C example. Okay, let's do C since they're on equal terms. Okay, so ring.c. Okay, so again, as usual, feel free to do the exercise. I'll shut up for now, so that if you want to concentrate, you actually can. So this would be a potential implementation, but we already see we have MPI send followed by MPI receive, so we know that potentially this can deadlock. Okay, let's see, MPI CC, ring, MPI -NP5, whatever, 8 without. And okay, it worked. So rank 1 received 0, that's fine. From rank 0, so basically the message received match the source, and that's indeed the case, so that looks good. If we run it again, it works. If we run it again, it works. So basically, in this case, the MPI implementation always chooses a buffered send, essentially. Okay, now I'm going to force it to do a synchronous send. Okay, so let's do that again. I compile and run. And now it deadlocks, as you can see. So just to show you what would happen if I were to actually have a deadlock, you might hear it in background. So my fan of my desktop is spinning up. If I do a stop here, then you see that in fact all my processes are running at 100% CPU time. So you might not notice a deadlock immediately because it seems that everyone is computing. Well, everyone is doing stuff, but nothing useful is happening. They're all just waiting, spinning for a message to come in, or rather for a message to finish. So basically, I'm going to stop it now. Okay. Hopefully my fan will spin down soon because this is annoying. So, although it doesn't seem to happen when I have a standard send, still it could happen because the standard send could go to a synchronous send. So just to illustrate, this was done using a blocking send and a blocking receive. Okay, so of course we can do the exact same thing in Fortran. Let me perhaps do that anyway. Okay, so this would be the same version in short term. So likely if I compile that, I would get the same behavior. So indeed, the MPI underlying MPI library is indeed going to call the synchronous version of this. So essentially, I don't see anything odd happening, but again, I could force a synchronous send, and then of course it would also deadlock. Okay, so that's nice. Now let's modify that, and let's make sure that rather than having a blocking send, we go for a non-blocking send. Question? 100% CPU usage. Basically because the MPI send is, well, the MPI S send, synchronous send, is going to continuously poll. Well, is it the send or is it the receive? That's a good question. Yeah, it's going to be the send, of course. So the send is going to sit there and wait for the receive to start. So it's continuously going to poll the network and see whether there is an incoming message. And of course, there isn't any, so it's just doing that very fast. And that means it's loading the CPU to 100%. Now, this depends a little bit on a couple of things. It depends on your MPI library. There are MPI libraries that are implemented in such a way that a spinning process, so waiting MPI send, synchronous send, is not going to have 100% CPU load. And also there are environment variables that actually can impact that behavior, that you can actually configure that should not happen. That's MPI iwait something something, for instance, which you can specify, for instance, for the Intel MPI implementation. So that depends a little bit what happens, but that's the reason the MPI send is just checking for incoming acknowledgements that the receive has started, and that causes CPU load. That's the idea. Okay, so let's change this a little bit, and let's go, for instance, for an iSend here, rather than a send. Okay, so now this is non-blocking, and of course I need an additional thing here, which is my handle, and which unfortunately it doesn't do for me automatically, so I'll have to check the documentation. MPI send. Okay, so I need to additionally specify a request, and in Fortran that request would be an MPI request. I'd have to specify that. Okay, so let's do that. We have, in addition to all this stuff, we have a type MPI request, yes, and we specify that as part of our MPI send. And now I forgot whether it's the last parameter or the one before the communicator. So let me check again, because I already forgot. So essentially it is the last parameter, as I already told. Okay, just to confirm that. Otherwise the compiler would have told me, since we're using type information here. So basically that would be my, well, what am I doing? My request. Okay, all right. So the send has been initiated, and I can do other stuff. The other stuff I'm doing in this case is nothing much. It's just doing the receive. But then before I can actually do something else safely, I should check whether the MPI request is in fact done. Okay, I could add status information, but again, I don't really care. All right, so that's the change I'd like to make. And now this actually is solved. So let's compile and run. And as you can see, it works. Yeah, you will say, okay, of course that works. It worked before, so why wouldn't it work now? Okay, but I can prove this because besides this being non-blocking, I can also make it synchronous. So now it's a synchronous call. And now, similar to the C version with the MPI S send, now, of course, if it could block, it should block. So let's see. And still, this works nicely. So this really solves the problem. Let's do the same thing in C, but with the receive. So just that we have the alternative view here. So now, of course, I'm not going to start with the send. I'm going to start with receive. And that's going to be an asynchronous, a non-blocking receive. All right. So everything else remains the same. The only thing is, if memory serves, I'm going to replace my status with a request. So I need to, where are my, well, I can do it wherever I want. So let's say here I have MPI request. Okay. And then I need to add that. And if memory serves, I just have to put it in place of the status. But let's check that. So then MPI I receive. Okay. So let's look at the C interface. This case, where's that? Okay, that's here. So we have, as usual, buffer count, data type, blah, 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 source, tag, communicator, and then indeed a request rather than the status. Why? Because you've already noticed in the Fortran version that I did MPI status ignore as a second argument to MPI wait. And I should do that because basically a send doesn't have status information. But now, of course, I have a asynchronous receive, and of course, the status would not make any sense in my, a non-blocking receive, so the status would make no sense. The status only makes sense when communication happened. So here, I'm going to put my request. Okay. Then we have MPI wait, and in this case, I could get the MPI status. In this case, I'm not using it, so again, I go with MPI ignore. But if I were interested in the status of the receive, this is the place where I would use it. So let's say, let's do it just for the fun of it. Let's also create MPI status in this case. Okay, and here I'll pass in the address of status. Okay, and just to use it, I can do something stupid from rank with tag %d, and then we have the whole lot here. Let's just flip that to the next thing, and that should be status MPI tag. Okay, great. So this again, let's just be contrary here, explicitly put a synchronous send. So with the synchronous send, this really should deadlock without the non-blocking receive. So if this works, it proves that the non-blocking receive actually does the right thing. So MPI cc ring.c. Whoop, did something wrong. Request, what's going on? MPI request, yeah, so. Of course, I have to pass in this by, well, I should pass in the address, let's put it that way. Okay, so, did I do this? Okay, let's check. Did I do the status right? Yeah, the status I did right. What is MPI wait doing? Well, it's checking whether the MPI receive is done or not. Because we can, of course, only use the receive buffer, which we're doing in the print statement, on condition that our receive is done. Our receive is, in this case, a non-blocking receive. So I have no guarantee that it's done until wait returns, because wait is now a blocking is a blocking function, of course, and it will block until the MPI I receive is done. So basically until I've got my information and I can use the receive buffer because there is something in it. So that's basically the idea here. So that's why in this case the MPI wait is really necessary. Okay, so let's see whether that works. Did I compile? No, I have to compile. Okay, I have to run. And as you can see, it works nicely. And this is also an illustration of using the status also a print tag. And indeed, that was defined as a constant, which was equal to 17. Okay, and of course, you can do the exact same thing in Python. That would, of course, be the same type of function calls. Okay. Any questions? All right. Yeah, so essentially we did all that, I think. And here we have an explanation, basically step by step. I'm guessing it's fairly clear what happens. So essentially this is a slightly different because we keep on passing information around. So essentially this is called as many times. We put a for loop around it with as many iterations as there are processes in our thingy, in our communicator. And basically that means that at the end of the day, we will actually compute the sum of all the ranks. So essentially, suppose that we have 3 processes, then our sum is going to be 3. If we have 4 processes, our sum is going to be 6, etc., etc. 0 plus 1 plus 2, 0 plus 1 plus 2 plus 3, etc. So that's the actual exercise. So it's easy to adopt this. Let's do that, for instance, in Python. Okay, so usual. Okay, new Python, better. Okay, then from MPI for Pi, import MPI. Okay, then we get communicator as usual. We also get rank, which I prefer to be my rank. Okay, we need the size. Yeah. Size, which is the size. Okay, then we need the send buffer. Which is my rank. Okay. The receive buffer we don't need to define up front. So now for iterations in range my size. So I'm going to do that my size times new. I'm going to compute the destination. Yeah, but I need to do that in the for loop. So let's do it here. So the destination is my rank plus 1 divided by my rank, and the source is going to be my rank plus 1 divided by, and that's wrong. We need to add my rank here, my size here, just to be sure that the right thing happens. Okay. And we have, I'm not going to call that sum here because sum is a function in Python. We don't want to overshadow that. Similar in Fortran, by the way. So we're going to do an com isend with a send buffer to the destination. Okay. And then we're going to do receive, and we store that in the receive buffer. That's fine. Okay. Now we have we can update the total, and we can actually do that immediately because we know that the com receive is only going to return when it has received the data. So we don't actually need the wait here. And then we can actually do the wait. So com wait. Okay. We're not interested in status information or whatever, so we can just do a com wait here. All right. And then at the end of the day, we can end this for loop. But we want the send buffer now to be the receive buffer. So basically, we want to send along the ring what we received. And then, of course, at the end of the day, then process my rank received the total. Okay, that was actually right. So that's annoying. Okay, so I'm accepting this, but I really like my double quotes to be single quotes. Okay. All right, so that would be it. Let's see whether it works. So MPI run -mp is 4, and then Python. What is it? Run.py. Okay. So if we do that, horrible things happen because, again, of course, I'm in the wrong window. So MPI run -mp4 Python ring.py. Okay, more horrible things happen. Okay, what did I do? Something fairly stupid, likely. Let's see, communication sent. Okay, I do something stupid in the I sent. Question is what? Okay, type error, message accepting buffer, or list or tuple. Okay, am I doing? I'm probably doing the wrong. I probably have to change this into that. Okay, that should be better. And I do have a receive, yes, okay. So that should be better. I have, of course, I'm not sending, wait, what is the, no, this should be lowercase, and that should be lowercase, I think. Yeah, because that's the stuff that doesn't support the buffer protocol. So I think that should be okay. Let's try again. No, that's still wrong. So let's indeed change this to uppercase. Let's change this to uppercase. Okay. And let's, oh, I don't need to background that. Let's do that again. And now still things are wrong. Okay, what's going on here? I sent. Yeah, now I have to wait. Now I have to be a bit careful. Attribute sent. Okay, this is. Okay, this was optimistic. I don't know the Python interface well enough to not get into trouble here. I would have to check the documentation. This is stupid. Let's see. Okay, non-blocking communication. That's indeed what I want. And then what have we got? We have. Okay, this is with the I sent. Okay, so we got destination. Yeah, and we have a wait. So okay, I'm ignoring the request. So that is pretty stupid because there should have been a request. I'm totally ignoring that, so that is not very smart. So that would be here. Let's try to spell that correctly. Okay, and I should call. I was already wondering because this looked fishy. Should call the request, but wait on the request. So that's definitely already a better idea. Then here, of course, we do two non-blocking calls. I would prefer to do only one. But maybe that's something that I can't do in I. Maybe I have to match them. Of course, this is not documentation, so let's go here for a second. That's more official. I don't want all this. And we have I send. Yep. I receive. And they appear to be all lowercase. Okay, so let's do this. Now let's see. Ew, bad. So now, but then likely, yeah. Now I have to match this here with lowercase likely. Yeah, and then okay, now it works finally. And each produces 6, which is indeed the plan. Okay, so I did a lot of things wrong, in the sense that I don't know the Python API that well. So essentially, now I'm using lowercase here, and this lowercase means that I can send an arbitrary object, so that's fine. The ISend will return a request. I do a wait on the request. And of course, given that I'm receiving an arbitrary object, that should also be with lowercase. And then, of course, my receive buffer is an integer, and that's converted automatically. Okay, we're finally there. And as you can see, we get the right result. So that's okay. All right. So we can do similar things in Fortran. It's just a for loop around the whole thing, or do loop in Fortran and a for loop in C. So perhaps let's not go there for now. And let's see whether we have other exercises to do. So this is an explanation, essentially, very nicely animated. So you see what's going on, and basically, I think it's clear what's happening. Okay, so in this case, I did two things. I did a non-blocking send combined with a blocking receive, and a non-blocking receive combined with a blocking send. Of course, I can have both a blocking receive and a blocking send as well. A non-blocking receive and a non-blocking send as well. So that's also possible. Then, of course, I would have two requests, and I would have to, at some point, wait for both. So let's, for instance, do that in Fortran. F90. Oh, this I shouldn't do. Let's quit. Let me quit this because, okay, so here's my C, here's my Fortran. This was fixed with an I send. Okay, so let me have a request here, and let's make that a send request and a receive request. Okay, so in the send request, obviously, I want the send request. Now I'm going to also make this an I receive, and then of course the status goes away and is replaced by the receive request. All right. So for the send request, I don't need to wait, but I need definitely to wait before I do the before I do the print, because I want the receive buffer. So I need to make sure that is filled. So I have an MPI wait. Up to this point, our good friend GitHub Copilot is correct, but actually I need to receive request here. Okay, then I can safely print. Then I still need my MPI wait on the send request. Why? Because I'm going to pack the whole thing into a do loop. Whoa, a do loop? Ah, come on. I need an additional integer variable I, which is going to be the number of iterations I do. So I get a do metaphor do. I is 1 to my size -1. That's very good. I'm going to put the whole lot into the do loop. Okay. I want an end do. Okay. I don't want to print in here. I want to print here. I additionally need total. Okay. I'll put total to 0. Okay. And I want to update total with receive buffer and send buffer set to receive buffer. Okay, so that would be the same thing now as in Python, but now with two non-blocking calls, both with a non-blocking send and a non-blocking receive. So now the order of the statements is not really arbitrary, because I can only do the update of total when I've got my receive request waited for, and I can only update the send buffer when the send request is completed. So this is the minimal thing I can do. So this would cost least, let's say, the least weight. Okay, let's see whether it works. So I'm going to compile. F90. Okay, I'm going to run that. Also with 4 processes and a.out. And as you can see, well, what did I do? Yeah, my print statement is not updated. I don't want to print a receive buffer. I want to print total. Okay. And of course, now the from doesn't make any sense, so we leave that out. Okay, and we compile again, run again, and we get, oh, that is not according to plan. What did I do? Total is 0. Yes, everyone is doing that. That's great. Send buffer is my rank. Okay. I'm sending send buffer. Okay. I'm doing receive buffer. That seems fine. I'm doing an MPI wait for receive. Okay. So that is likely not a good idea. Let's do this. And let's try that again. Okay, and let's run them. And that is still not okay. What am I doing? Receive buffer, send buffer is receive buffer. And I'm doing that. From 1 to size preferably. Okay. So that was likely the actual problem. Let's run. Yeah, so now everyone gets 6. And I'm still convinced that I actually can do it this way to minimize delays. So let's verify that I'm correct. And I'm correct. Okay, so yeah, I did one iteration too few. And of course, yeah, that was not the intention. But yeah, that's with one starting thing, etc. in Fortran. Sometimes you get confused. Okay, is this more or less clear? Any questions about this? All right. Now, okay, so that's the first exercise, blah, blah, blah. Okay, we know. So we have used quite a number of handles here. For instance, MPI com_world, also for data types, MPI int or MPI integer in Fortran. And also that would be a data type, essentially. And in Python, yeah, it's automatic. Type would be MPI float, for instance, for double precision number. So there's also memory for the communicator. The type is MPI com, etc., etc. Okay, so the request handles, they are used for non-blocking communication. You've actually seen them. So it's an MPI request in C and C++. It is type MPI request in Fortran, and in Python, of course, it just works. Okay, so the value is generated by the non-blocking communication routine, so by the MPI I, send, receive, whatever, and it's used and also released in MPI wait. Okay, so you can do a non-blocking synchronized send. You've seen me do that in the Fortran version to really convince you that actually that deadlock was gone. And in Python, you can also do that with MPI I send or MPI I send lowercase if you are not sending buffers around. Okay. So what you have to really understand is, and let me show that in the source code. So what I can do after doing an I send is modifying the send buffer. So this I shouldn't do until the wait completes. And similarly, I shouldn't use the receive buffer in an MPI I receive before I've done the wait. And I'm really doing that here very nicely because the call to MPI wait on the receive request actually happens before I use it for the update of total. And I'm going to modify the send buffer And I'm only going to do that when the send request is completed. Of course, remember what we said when we started talking about non-blocking operations. If I have an MPI send, an MPI I receive immediately followed by an MPI wait, this is exactly the same as an MPI receive, so a blocking operation. So essentially, this is fairly useless. However, I just wanted to show you that you can, in fact, use non-blocking operations for both send and receive and combine the two. But again, this is useless since we have an I receive immediately followed by a corresponding MPI wait. So this is really, really useless, but just for illustration purposes. Okay. Basically, what we would have to do, and that is something that we actually have to be a little bit careful about. In fact, in Fortran, we made a mistake. In Fortran, actually, we should have declared that our buffers are asynchronous. So this is not really correct. What I would have to do is to say, okay, my send buffer and my receive buffer I should declare as integer. Yeah, almost, but asynchronous. Okay. And why do I have to do that? I basically have to do that because it tells the compiler, at least if it's a recent compiler, to ensure that these variables are not stored in a register, because otherwise I can actually get results. And we will go into much more detail about that later on. You see that actually I should have even included something more here. So basically, I should have verified whether the async is actually protecting a non-blocking communication. If that's the case, I have no problem. But if that's not the case, then I should actually deceive the compiler by using the buffer in a function call. In that case, the compiler is not free to put buffer in a register. It can't do that because it's going to be used in a function call, well, in this case a subroutine call, and basically the right thing will happen. So, in fact, what I should have done is, in this case, after the wait, I'd have to put if not MPI async protects non-blocking. And as you can see, GitHub Copilot is not always your friend when we're really talking more sophisticated. Oh shit! Non-blocking. Come on. Okay. Then I don't want to call MPI wait. What I want to call is MPI fsync, and I don't want to call it that way. I want to call MPI fsync register. On our, not our send request, but on our receive request. Okay, well, receive buffer actually. Okay, so as you can see, GitHub Copilot here doesn't have a clue what I'm doing. So just to show you that that can be dangerous. And here I need send buffer. All right, so this is essentially protecting us against old Fortran compilers that would not know that async actually ensures that things don't go into a register. So it's actually quite important that you put this line there to ensure that you don't have trouble with this. So just out of curiosity, let's see whether this compiler supports it. Actually, I know it does. So if that happens, I'll print not okay. Or not protected. All right, so let's compile that. That was our ring, Fortran, of course. Okay, I forgot an end. Okay, syntax error. Yeah, that is a dot. That should be, of course, a comma. Okay, this should compile. No. And if, then, okay. Forgot the end if. All right, never. Still not really. MPI async protects non-blocking. Yeah, well, what did I do wrong? MPI async protects non-blocking. Typo. It's protects, not protect. And of course, go to do that twice. Okay. Finally, so that should work. Now, what's going on here? MPI fsync reg. Reg, yeah. Did I put a C there? No. Double underscore. That's of course fairly stupid. Okay. Let's try again. Oh, great, now it works. All right, and let's execute that again, just to see whether indeed what the value is of this particular variable. So with this compiler, I'm fairly certain that it's actually okay. No, it's not okay. Whoa. Okay, so now I am surprised. Okay. Mm, 11.4, and it's not supporting this. Ooh, that's not cool. That's so very not cool. Okay, let me switch compilers. And let's go to the most super recent one. Wait, where is my switch compiler script? Should be somewhere. That I can't seem to. Would I only have that? Yeah, probably I only have that on my laptop. Yeah, okay. Let's not go there. Yeah, of course. I probably won't even have GCC 12 here. I do. Only it's not a default. Okay. All right. Let's assume. Okay, let's just be disappointed. But basically, that means that it's really even more important than I thought. Basically, you have to really make sure to do this, because otherwise you may have issues. And we will discuss those in more detail later on when we talk specifically about Fortran. Okay. Yeah, that's my essentially my remark here, which I made not for I send, but rather for I receive. Okay. So basically, this is also a remark I already made. Essentially, if you have a send, yeah, nobody cares about the status because there is no status in a send. But the status in the MPI wait is there because you actually are interested in the status, potentially, of the receive. And that's only there when you do the wait, as I already explained. So I think we also discussed all of this. So let's not go there. So we have blocking and non-blocking. And essentially, for every blocking operation, there's a corresponding non-blocking operation. So we have an MPI I send. That's a standard MPI send, but non-blocking version. MPI I synchronized send, MPI I buffered send, and MPI ready send. And of course, all of them are essentially similar to their blocking counterparts. Okay, so of course, in this case, it doesn't influence the completion time of the non-blocking operation, but it will influence whenever MPI wait or MPI test completes. So that's important to realize, of course. Okay, so completion we can test with MPI wait as we have done up to now. So you specify request handle and status, but you can also do an MPI test. And this, of course, is something that you would do, for instance, in a while loop. And as long as the test says false, then you continue your while loop, you continue to do operations. And as soon as it's true, then you can stop your iterations. So notice that those are functions, again, that you need to specify the flag to. And then, of course, in Python, you just do the MPI wait, or you do the MPI test, and the MPI test is, in fact, going to return the flag as such. Okay, and the status is going to be updated. Okay. So you have to create the status in advance then. All right, so you have to wait or you have to test. And test you will use if you're looping and doing stuff meanwhile. Okay. Then, as I mentioned, you can have multiple blocking, non-blocking communication going on. So, for instance, you could say, okay, I'm going to send asynchronously both left and right. So then you would have, non-blocking both left and right. So you can have multiple outstanding non-blocking communications. And then you can wait for them individually, or you can wait for any, wait for all, test for any, test for all. You can wait for some, which means at least one message. Okay, so these are options which can be useful at times. What you have as a function signature is essentially that you pass in an array of requests. So let's have a look at the menu page for that. So MPI wait all, for instance. Do I have to? Okay, I have to just type one. Okay, as you can see, we have a count, C, and then we have an array of requests, and of course also an array of statuses. Of course, in modern Fortran, it's the exact same thing. But we have to specify the count. In Fortran, basically, there's no reason to, because a Fortran array knows its size, so that's not a thing. But of course, in C, an array is just the address of the first element. So essentially, that means that you have to specify the count if that needs to be known in the function, and of course MPI weight all or MPI weight any has to know that. Okay. Then other MPI features. We also have a send receive in one routine. So that's MPI send receive and MPI send receive replace. And in MPI 4, there is a non-blocking version of those as well. So basically, what it does is it does an MPI I receive, then a send, then a wait in one routine. So that's basically the idea. So essentially that is for Halo Exchange. This is quite useful. And as you can see, we're going to do that later on when we talk about derived data types. Okay. And you also have that in a non-blocking way. Okay. So MPI send receive might lead to serialization and to deadlock. So that's why the non-blocking version of this was added, so that you can also avoid that, and that again you can do many such communications requests in parallel. For instance, you can use it to do Halo exchange with your left neighbor, with your right neighbor, up neighbor, down neighbor, and so on, and all of those can be done non-blocking. Meanwhile, you can do other stuff, and then you can have the corresponding weights later on. Okay. Options for performance. Essentially, and this will occur many times, what's the best combination? Should you do an MPI I receive and an MPI send? Should you do an MPI I receive and MPI I send, or any other combination? Actually, nobody knows, in the sense that, yeah, okay, you have to check on your system what is going to be fastest. So MPI tries to be, well, is source code compatible, but performance is not portable. So whatever is most efficient on the system you're developing on need not be the most efficient on another cluster. So for instance, if you do develop on, let's say, some tier 2 system, and you move your code to tier 1 or to Lumi, then that might give different performance. You might have to do a different combination of those in order to get the best performance. So it's something that you might need to experiment with, which is best for your particular application on a given platform. Okay. So when you use non-blocking operations, essentially to prevent serialization and deadlocks, also to get real overlapping of several communications, or of communication and computation. However, there is some caution necessary there, because your MPI implementation needs to support that. And we'll talk about that in more detail when we talk about non-blocking collectives. There is a slide there that talks about that. Okay, so specifically for Fortran, what's going on here? I already mentioned the code as it was originally was not correct. And that's the same code we have here. So we have a call to MPI I receive. It uses the buffer. And then we have MPI call wait. We have the request handle, and we reuse the buffer. Okay. So in this case, the buffer, as you can see, is not part of the argument list of MPI wait. It's used in MPI I receive. It's used in the write statement, but not in the intermediate code. Of course, it shouldn't. If there's anything between the MPI I receive and the MPI I wait, we know that we can't use the buffer, period. Okay, but this seems safe at first sight, but unfortunately it's not. because it could be compiled as follows. So basically what could happen is we have the call of MPI I receive with buffer. Then the buffer could be stored in a register. We could call MPI wait, and then what the write statement would use would be that register. While during the time that wait was completing, actually buffer was changed. But the compiler doesn't know that. The compiler can't know that that is the case. So it's free to actually, for performance reasons, store the value of buffer into a register. Okay, so this is what might go wrong because the compiler has not enough information. Okay, so basically that means that the variable buffer is updated, but of course the corresponding register variable is not updated, and hence we get simply the wrong result when we do the write statement or when we do further computations using the buffer. Okay, or what we think that the buffer is. All right, so this is really a problem that does arrive in Fortran because Fortran compilers really optimize very aggressively. So that's something that C compiler is not allowed to do. A Fortran compiler can actually do that because in, let's say, Fortran semantics, this would be perfectly okay. Of course, it's not okay. And the simple thing to do, we hope, is to add asynchronous as an attribute to our buffer type declaration. And that tells the compiler, at least a smart compiler that supports this, which apparently gfortran doesn't do, at least in version 11, not to do these kind of things. Don't put it into a register. Okay, so if the compiler does the right thing, asynchronous as an attribute to your type declaration is enough. Right, except that if the compiler is clueless, then of course it's not enough. So in that case, what do? So indeed we add this if statement, which basically checks whether the MPI async is going to protect non-blocking. If that's not the case, we have this function call here. And given that this function call is here, it actually means that the compiler is no longer free to put buffer into a register. It will need the actual value which is stored in buffer because it's going to pass into a function call. And then we are sure that actually the right thing happens. So basically what you need is a Fortran compiler that is compliant with TS29113, which is basically something in the, well, a request essentially in the Fortran specification. Okay, and then if that's the case, then the MPI library can set this to true and the right thing will actually happen. Okay, in that case, again, the Fortran compiler is very smart and it will just remove the entire if statement and the call to MPI fsync register. So that's what the smart compiler is going to do and the smart MPI library is going to do. However, unfortunately, that's not going to happen if you have a stupid compiler and then you have this call to MPI fsync register, which is not doing anything, but it's there in order to protect our buffer variable from being stored into a register. So that's basically the idea. And again, the problem is that the buffer is not part of the MPI wait parameter set. So that is bloody annoying. And that's what I mean, that it's one of the few cases where you have more issues in Fortran than you actually have in C or C++. Okay, so that is annoying. We can check what one API now does nowadays, but let's not do that now. So essentially, there's also another workaround in older MPI versions, but okay, let's forget about that. Okay, so this would be exercise 2, but I think we actually already did that because it's the same thing, but now with a receive, well, with an MPI I send rather than an MPI I receive, but we already did that in one of the versions of our exercise, either in C or in C, or in Fortran or in Python. Some we did that already. Okay. All right. Yeah, that's also quite interesting. Does it actually work when we started with one MPI process? I don't know. Let's check. So MPI run -np and then our A out. Okay. So in a way, it does the right thing. Essentially, we have we have 0, which is indeed the sum of all ranks, and of course there's only a single rank with rank 0. So it seems to do the right thing, which is nice, but which is weird. Why does this work? I mean, I'm sending something. Okay, what's destination? What's source? Let's see. So rank is going to be 0, size is going to be 1. Okay, so let's check what the destination is. We have my rank plus 1, so that's 1, and we compute modulo with respect to my size. So yeah, that's going to be 0. Okay, so the destination is 0. What's the source? Well, we subtract 1 from rank, that's -1. We add size, which is 1. Okay, modulo my size, which is 1, is going to be 0. So destination and source are both 0. Okay, so essentially it means I'm going to send something to myself and I'm going to receive it from myself. A bit pointless, but it's okay. So essentially, yes, you can send messages to yourself if you really, really want to. Okay. And then I receive implied instead of I send. So we already did the advanced stuff. And then again, we have a quiz. Again, I would suggest have a look at it. And if you have questions about it, let's discuss that tomorrow. Okay. All right. So, let's say to conclude for today, because I don't think I'll manage to do something in addition to this. Let me just check what the next is. I'll come back to these slides. But I want to know what the next chapter is. No, collective communications for tomorrow. I'm not going to do that now. Okay, so let's talk briefly about the Fortran interface. So non-Fortran people can tune out if they want. Given that, the link for the session of tomorrow is the same as today. So you can just reuse that link. Again, we start at 10. 3 sessions again, 10 to 12, 13 to 15, 15 to 15:30 to 17:30. So the plan for tomorrow is exactly the same as today. By tomorrow, there will also be recordings online, normally of the sessions of today. So if you already want a link, let me know by tomorrow. Okay, so let's continue for the Fortran people. There were issues. Let's not go there. I mean, MPI 1, who cares? That is basically for historical reasons. So there is not much reason to talk about that. Things started out with a header file, which was mpif.h. That's deprecated in MPI 4.1, which basically means that you can still use it, but you shouldn't. And the library should warn that you should not do that. Okay. Anyway, don't do that. I mean, it's really not a good idea. So then we had the MPI module in MPI 2. Again, unless you need that for historical reasons, don't do that, because it means that, of course, a handle, for instance, is just an integer. So we have zero protection against swapping orders of order of the parameters. Also, you always have to remember to have this error checking. So that last thing. Okay. So basically, we have the problem which we just discussed. Let's not go there. We already know that. Enter MPI F08, and of course we discussed many of those already, many of those issues. So essentially, there is a different way of dealing with these non-blocking routines. Okay, and the I-error is now optional, and of course, maybe even more important, actually, we have type checking now, so that is definitely a good thing. Okay, so basically, everything is still sort of supported. MPI next is not going to support MPI f.h anymore. I hope no one is using it. Okay, routine declarations, we already mentioned that. So basically now there is proper type information on each of those arguments. So swapping them around is not going to work. For instance, if you would swap the data type and the communicator, your compiler is going to say that you can't do that. So that definitely helps quite a lot. Okay, the asynchronous, etc., we already discussed, so that's not a problem. So why is this added? That actually solves strided array problem, which we will discuss in a minute. Okay, and this is also asynchronous in this case, because this is an iReceive. So basically, of course, in the implementation itself of iReceive, the right thing happens. Either the compiler supports TS29 whatever, then everything's fine. Otherwise, we have this MPI fsync register call, which protects it. But that's implementation. Okay. We also have intent. So basically, that means if you, by accident, for instance, pass in something that's a parameter, that's not going to work. Basically, a constant. Okay. So the nice thing is also that status is now a Fortran user-defined type. I prefer the term user-defined type rather than derived type, but okay. And that also helps a little bit because it makes your code much more transparent. And I-error went optional, so this we already know. A nice side effect, which I didn't mention yet, is that in fact you can use keyword-based argument lists. And that's nice. That's something you can do in Fortran and that you can't do in C. Of course, you can always do that in Python, but it's nice because now we don't need to remember the order of the arguments. We can just use the name of the parameter. So If you can't remember where the destination comes before tag or vice versa, just use keyword arguments and you don't have to remember. The right thing is going to happen. So that's actually rather nice. Check the documentation for the names of those arguments. They're just in the man pages. So that's of course easy. Of course, yeah, okay, outdated documentation. I really think you can find documentation for MPI 2.2. Okay. Anyway, so MPI status. So as was already mentioned, this would be the old state of affairs, which is really, really ugly. So now it's much nicer because you can just use status percentage, MPI source, MPI tag, MPI error. So that's in a way much nicer. Okay. Handles now are typed, so that's good because previously for Fortran everything was an integer. Yeah, each handle was just an integer. Now it's specific types, so that's of course quite a lot better. Okay, that also means that you can in fact properly handle comparisons between handles. So basically you can just use the equality operator, and those are overloaded for the specific types. So that's actually rather nice. You don't really have a difference here. So that's actually quite good. Okay. So you can check the quality of your MPI library, for instance, by testing what is this MPI async protects non-blocking. So this we already tried out, and there are a few other things you can check. I hope they are listed here, but no, not really. Okay, let's skip that. Yeah, this is the non-blocking thing again, and basically we know that now. We've already done that. Okay, and the rest seems to be skipped, so we're going to do that. All right, there are some best practices. So essentially, make sure to not use include, okay? Make sure to use MPI F08, I'd say, and then okay, let's not go there. That is something that is provided by your MPI system anyway. And then, of course, use typing rather than integers. Okay, other things interesting. Yeah, this we already mentioned. Don't forget this in your Fortran code because otherwise you just will get the wrong results. So be careful not to get confused there. Okay, that is skipped again. Detailed description of problems. So basically, there is a lot of potential problems with code movement and register optimization. So you need to be aware. I'll mention several of those during the rest of the session. So essentially conclusions. Okay, I don't think we need to go there. You have to be careful with sub-arrays, whether they're supported or not. So that is important. But apart from that, and I'll come back to that later on, we are actually done with what Fortran has as extra problems with respect to C and C++ and MPI. Okay, so are there any questions? If not, we'll conclude for today. I'd say if you like, have a look at the quizzes. Try some things out by tomorrow. If you have questions, let me know. tomorrow, and then we'll discuss that. So we will conclude. We will continue with collective communications. So that is a reasonably sizable chapter. So that will definitely take us the morning, maybe including error handling. Then in the afternoon, we'll talk about most likely about groups and communicators, and probably virtual topologies as well. And maybe we'll start on one-sided communication. We'll see. But I might swap the order a little bit, because I would prefer to talk earlier about derived data types. So we'll see. Maybe I'll swap the order a bit. Okay, that was it for today. I wish you a pleasant evening, and I'll see you tomorrow. Unless there are questions. Thank you. You too.